In this video tutorial, we will be looking at how you can construct in simulation the circuits that you will be analyzing in your Electronics 2 lab. In this video in particular, we will be concentrating on the Class A amplifier. And then there will be a follow-up video for the second part of your lab, which will entail building a Class B amplifier. When it comes to active devices, the simulation can only be as good as the model that you are given for the device in question. In this case, we've got a model for the device which was produced for SPICE, which is a very old simulator, but can be imported into Microwave Office with the appropriate modifications. I've done the modifications for you, so all you will need to do is get the file from Blackboard and then import it into Microwave Office, and this will give you a model for the transistor which will replicate the actual transistor that you're using in the lab as closely as possible. Every time you import a new model, you have to do something to verify that the model appears to be behaving in the right way. When it comes to transistors, the best way to verify that a model is behaving appropriately is to plot the relative IV curves. So first of all, let's create a new circuit schematic, and we'll call it IV curves. And then we'll just come back to this in a moment. What we need to do next is to import the model that we've got for our transistor. In this case is an NPN transistor, and if I just right click on netlist and then choose import netlist, then I can simply pick the file which I need to import and contains my model. In this case, your file will be a text file called ZTX651, which is the model of the transistor you will be using, and then click on open. Now, since your file is simply a text file, the simulator will ask you what kind of format is this text file in. And the one that you have to choose, and be careful with this one, is HSpice files, but you have to pick the obsolete option because the model is quite old and hence its format, it's one that is contemplated only in this option. And then click on OK. Now you can see that AWR tells you whether you want to swap the first two nodes. This is a difference between the way that the simulation in SPICE worked and the way it works in Microwave Office. The best way to do is to just say yes, and this has advantages which we'll see soon enough. So you import your model, and then when asked, when prompted, whether you want to swap these nodes, you click on yes. Now you can see that there is a text file that's been created by Microwave Office based on the file that we've imported, and now this represents an NPN transistor which can be directly used in our simulations. So let's go back to our schematic. Now, how do we get the transistor to appear in our schematic? As you know, when you want to get an ordinary element, which is part of Microwave Office, you just press Ctrl L and you get a list of elements coming up. In this case, you can get this model that you've imported in two ways. Either you click on the subcircuit icon in the toolbar, and then this will give you a list of subcircuits and models that you can pick from. In this case, of course, we've only got one because it's the only one that we created. Or, equivalently, you just press Ctrl K, and then you get the same dialog window appear. You just click on OK, and then you will get a box like so, which contains the model that we've imported. If you want to see what's inside the box, you click on the box and then you click on the down arrow up here that says Edit Subcircuit, and it'll show you what's inside that box. Now, the problem that we've got is that we've got pins 1, 2 and 3, and now you don't know which one is the emitter, the collector or the base. Now, this is why it's important to allow AWR to swap the nodes the way it wants to do. Because if you do that, what you can do is right-click on this box and go on to Properties, and then select the Symbol tab, and then under the Symbol tab there will be a BJT symbol, which is this one here. BJT with 3 pins, and is the one that the system uses as a default. So once you've assigned a symbol to your subcircuit, then Microwave Office will automatically label the various terminals in the correct way. So you know the B is the base, and C is the collector and E is the emitter. And this makes life a lot easier. This is a general rule that works for any subsequent file imports that you should carry out. So we mentioned that first we want to verify that this model is working correctly and that this assignment of pins, for instance, has been done properly. This is quite easy to do. We simply plot the IV characteristic for this transistor. How do we do that? Well, there is an element in MacroOffice that allows us to do that very simply. So press Ctrl L and then search by name. You can see that the funnel is just next to the name heading here. And then you just type IV curve I. And this is the element that we'll need for our IV curve plotting. So now we have to select a range. Well, we'll select a range which reflects what we're going to do in the experiment in the lab. So we'll have a voltage at the collector which goes between 0 and 12 volts, and we'll do this in steps of 0.1 volts. And then in terms of the current, we will start with 0 milliamps, of course, and then we will go up to 500 microamps, which is 0.5 milliamps, in increments of 0.1 milliamps. So the current that you will be injecting into the base during your experiment will be probably of the order of 200 to 250 microamps. So this should cover it. So then we connect the swept terminal to the collector and then the stepped terminal to the base. Then the last thing left to do is to put a ground in the emitter. And what happens here is that the stepped terminal creates different bias conditions by injecting different base currents into the transistor. And then for every bias condition created by each of these currents, then the swept terminals will sweep the voltage of the collector all the way between 0 and 12 volts and hence create a full curve. This is much easier seen on a practical level than explained. So let's get on to plotting these IV curves. We go on to graphs, we right click, create a new graph, and then we'll call this IV characteristic, and then we simply right click, select add a new measurement, and then we go on to nonlinear, current, select IV curve, and then we need to select the schematic from which this comes, and this is IV curves, of course. These other two parameters can be left as they are. Effectively, all we're saying is that for the x-axis we are using our VCE voltage as it is customary for the IV curves, and then we are plotting all traces for each bias condition. So then simply click on apply and OK, and then simulate. You can see that the IV curves look exactly as they should, and also you can see that this transistor looks relatively realistic because, for example, we have the early effect which is represented by this model. So this is quite a good model that is giving us also the effects that normally in an ideal transistor you shouldn't see. These lines should be perfectly flat, whereas they have some degree of slope, which is due to the early effect. Now for a Class A amplifier. The first thing that we're going to need to do is work out the bias conditions. I am not going to do this calculation for you, but I will tell you what the result should be. Let's go back to circuit schematics, right click, create a new schematic, Class A amplifier. And now, yet again, what we need to do is get our transistors in here. We can simply go back to our IV curves schematic, select the transistor as it is, press Ctrl C, and then go back to the Class A amplifier schematic, press Ctrl V, and this gets us the transistor. If we hadn't done things this way, we may have had to reassign the symbol to the transistor, so it's a good way to do it. Now we can replicate the schematic in figure 2 of section 3.1 of your lab handout. And to do this, we simply press Ctrl L, and we fetch a couple of resistors which you can find under RES, and then we place them on the schematic to replicate the figure that we've got on the handout. You can simply select the resistor, press Ctrl C, and then Ctrl V multiple times to create as many resistors as you need. Okay, the other thing that I like to do, and it's very good to do, is to change the IDs of the various components. So this in the schematic on the handout is R1, so we'll call it R1. This one is R2, so we call it R2, and this one is RE, so we'll call it that. So here the handout shows that there is a current meter in series with the collector. However, when we're working at DC, Microwave Office has got other tools that we can use to measure currents and voltages. So just for the purpose of biasing the transistor, we won't need to insert any voltage or current meters, and we'll see soon enough how the voltages and currents can be measured. So the next thing that we need to do is insert a ground reference in the emitter and then connect everything together as is meant to. Now what we need to do is insert a voltage source to power up our transistor. So again, press Ctrl L and type in DCVS. Place that on the schematic like so. Of course, use a ground reference and then connect it to the collector and also of course to one side of R1. Then you change the value of this voltage source to 12 volts, and then the last thing left to do is to assign the correct values to our resistors. Now the emitter resistor is given to us, and that's 150 ohms, and then when it comes to R1 and R2, you should be able to calculate what their ratio should be, and you will find out that the ratio is 2.1. So R2 will be 2.1 times greater than R1. Since this is the case, what we can do to be able to vary the resistors proportionately all the time is simply declare a variable, and we do this by clicking on the equation button in the toolbar and then clicking on the schematic. We'll give a name to this variable. We'll call it R1, and we'll assign a value to it of, for example, 390 ohms, and then the value of R2 will simply be 2.1 times R1. So the value of R1 will be the variable R1, and then we need to assign a value to R2, which is about 2.1 times R1. Now we need to find a way to look at voltages and currents for our circuit so that we can verify whether we've achieved a collector current of 50 milliamps, which is what is asked in the exercise. To do this, we simply right-click on the Class A amplifier schematic and then go on to Add Annotation, and then select DCIA, which gives us the current for all elements, and click on Apply, and then DCVA N, which gives us the voltage for all nodes. Apply and OK, and then simulate. Now you can see the voltages and currents for all elements, and you can see that our collector current is about 49.1 milliamps, and we've got a current going down a potential divider which is about 10 milliamps. We can also see the current flowing into our base, which is roughly 222 microamps. Now if you find that the font for these annotations is either too small or too big, you can simply go to Options and then Environment option, and then for example you can select the Schematic Annotation tab, go on to the fonts and decrease the font if you so wish. It's 14 now, we can change it to 12. And then you can see that things perhaps are a bit more legible. You can do this for any elements of the circuit. You can see that we haven't got exactly 50 milliamps, and this may be because I've approximated the ratio of R2 over R1 to 2.1, although it was just slightly over. So for example, I could pick 2.2 and see if this makes things better. You see that now we are really closer to 50 milliamps. So it's also a matter of how you approximate your calculations as to what result you get for your simulation. Of course, if you think about it, the transistor is a current amplifier, so the current that you inject into the base then gets amplified and comes out of the emitter, amplified by a certain factor. So the more current goes into the base, the higher the current that would be going through the emitter and the collector. So if I increase the value of R2, as I've done here, then R2 will oppose more resistance to the current that comes from R1, and hence more current will flow into the base. Because more current flows into the base, due to the fact that this resistor is now higher, then you get a higher current coming out of the emitter and collector terminals. When it comes to choosing the values of your resistors, of course you know that the ratio must be 2.1 or 2.2. However, you can choose different values for the resistors whilst maintaining the same ratio. And it is a matter of how much power you are prepared to dissipate in your bias network. For example, you can see that at the moment I've got about 10 milliamps going down here, which is quite a lot. And this is to produce a current which is only 225 microamps. So the rule of thumb is that when you use a potential divider to create a certain voltage at the node between the two resistors, the current that comes out of that node should be at least 10 times smaller than the current that goes through the potential divider itself. In this case, this condition is met by a long way. So what we could do is make our resistors bigger and hence have a lower current going down our potential divider. If we do that, then we will be dissipating a lot less power in our bias network, whilst keeping the bias of the transistor at the level that we want it. So, as you know, in Microwave Office, you can simply click on the Tune tool and then click on the variable of interest, in this case R1. Of course, by changing R1, we'll also be changing R2 because the two are related by an equation. And then we open the Tune tool. And with the Tune tool, we can change the value of our resistor and see what happens to the various currents and voltages in real time. Now, let's say that for our minimum we choose 300 ohms, and then for our maximum we choose 3000 ohms, which is 3 kilo ohms. And then we can go up in steps of about 100 ohms. I think this is more than reasonable. So let's see what happens as I move the slider up. You can see that the potential divider here now is drawing a lot less current overall, and hence this dissipating less power, and we are getting a base current here that is slightly smaller than what we had before, but we're still achieving 49 milliamps at the collector. So really the advantage of having a higher resistor here is simply that the power that the bias network dissipate, which would be the voltage from the power supply times the current that flows through it, will be much lower. And hence, since this power doesn't go into the signal directly, you have a much more efficient amplifier overall. So we could set these resistors to whatever values we think is suitable, whatever value gives us the right compromise. But of course, we have to make sure that we don't exceed the correct ratio for our potential divider to work properly. For instance, if we decided to have a value of 10 kilo ohms for R1, you can then see that things have changed quite dramatically. Now the overall current that's going through the potential divider through R1 is actually 0.5 milliamps. But you remember that we needed about 0.2 milliamps to go through our base to get the right bias current at the collector. So now you can see that our equations don't work anymore for the potential divider, and the only way we have to sort things out and get more current to flow through the base is to increase the value of R2. So now, for example, the value of R2 was 22,000, and we can tune this value so as to achieve the right base current. You can see that as we increase the value of R2, then what happens is that R2 opposes more resistance to current flow. The current that goes through R1 then will see the base of the transistor as a preferential path, and hence more current will flow through the base. We go back to having about 0.2 milliamps into the base of the transistor, and hence at the collector we re-establish a higher current. All the same, it is advisable not to have too high a value for R1 and R2. So try to choose a reasonable compromise and make sure that your bias conditions are met. So I will not choose the values of R1 and R2 for you. I will revert them to what they were initially. So we had 390 for R1 and R2 was 2.2. times R1. Although, as we've seen, in this case we draw quite a lot of current from our power supply just for our bias network, and this is relatively unnecessary. We could choose resistors that draw less current and hence allow us to have a higher efficiency. The bias of your transistor doesn't translate into power into the output signal, and hence the more power you waste in your bias network, the less efficient your amplifier would be. Now, part 3.11 of the exercise asks you to set the power supply to 12 volts and find the quiescent values of the base voltage, the emitter voltage, and the collector current. Of course, you can read this directly from the schematic, having set up the annotations correctly, and you can see that VCC is of course 12 volts, VB, which is also called VBQ, it's about 8.2 volts, VE, which is the emitter voltage, is about 7.5 volts, IC, which is the collector current, is 49.9 milliamps, and then VBE, which is VB minus VE, you can easily calculate. Another way to measure the voltage between two nodes is to have a voltage meter inserted between the base and the emitter. So if you wanted to do that, you can simply press Ctrl L and then find V underscore meter, and then you can place that like so. And if you want VBE, VB will be here, and VE of course is over where the emitter is. And so we'll just go around a little bit and we set up this sort of arrangement, and this will give us the VBE voltage. But in order to see the voltage across the meter, we have to add an extra annotation. So you go back to Class A amplifier schematic, right click on it, and then go on to add annotation and pick DCAM. Then click on apply and then OK. And then when we simulate, we can see exactly what voltage our meter is measuring. Okay, so now we've done pretty much everything we needed to do in terms of bias. So what we can do is go back to our project tab and delete all the annotations from the circuit schematic, so they're not in the way of what we will be doing in a moment. We can also remove this voltage meter here. Now here's the thing, when it comes to biasing the transistor, you're working at DC, and hence we didn't really need the capacitors shown in the schematic. But if you need to put an AC signal into your transistor, then you will need to have capacitors, which are open circuits at DC, to avoid your signal affecting your bias network. So let's put those in. Let's press Ctrl L, type in cap, and we have one here, and then one there. The default capacitor units are microfarads, which works well for us, since this is what we need. So we simply need to set both of these to 10 microfarads, and we're in business. And then what we need to do is have a signal generator on the input and a load on the output, so we can create a proper amplifier. So press Ctrl L again and choose ACVS and AC voltage source, which you'll then be placing at the input like so. You need to have a ground connection, of course. And then we need a load, so we'll just press Ctrl L, get ourselves a resistor, turn it around by right clicking, and then place a ground at one side of it, and the other side will connect to the capacitor. The load resistors, of course, this is called RL, so we'll call it RL, of course. And then we'll set its value to 100 ohms, which is again what is prescribed by the exercise. Now, it's very important to stress the reason why we have the capacitors in here. If we didn't have capacitors, which act as open circuits at DC, when we connect our voltage source, some of the current that should be going solely through our potential divider and into the base may flow out and go into our source, and hence this would alter our bias. When our source is producing a signal, this would also alter our bias all the time as the signal goes through the various cycles. So it's very important to have these capacitors here to preserve the bias conditions that we've created. Those bias conditions are DC. DC does not go through capacitors, and hence this is a sufficient protection. Similarly, when we connect a load here, we don't want this load, this resistor here, to affect the bias. If we didn't have the capacitor, some of the bias current would be flowing through the load resistor instead of going through the emitter resistor. Now the exercise asks us to have a signal of 2 volts peak to peak. The input signal here is showing a magnitude of 1 volt. This is V peak in macro office. So if it's 1 volt peak, it's 2 volts peak to peak. And hence we don't need to change this value. This is fine as is. The thing that we need to change, however, is the frequency. And as you may recall, the frequency in macro office is not set locally, but is set globally. So we double click on project options, and then we select our units to be kilohertz, and then we select single point. We put 3 kilohertz down, create, and click on apply. And now you can see that here in the current range we have a single frequency which is 3 kilohertz, which will be the frequency at which our AC signal generator will operate. Click on OK. You may be wondering whether I've made a mistake by saying that our input signal generator has already got the correct amplitude to produce a 2 volt peak to peak signal. And that is because the exercise is actually asking us to produce a 2 volt peak to peak signal at the output. As it happens, this type of configuration has 0 voltage gain. So the voltage that we see at the input and the voltage that we see at the output are identical. The reason for this is that the amplification in this amplifier is at current level. This is a current amplifier, but as it happens, it does not change the voltage. The fact, however, that we have the same voltage but different currents means that impedance being current divided by voltage, this amplifier acts as an impedance buffer. It can transform a high impedance into a low impedance. So we need to be able to plot our input voltage and our output voltage. There are various ways of doing this. As you may have seen in previous videos, we can use a measurement probe, which is this thing up here. We can use our voltmeter as we did earlier, but this time it will measure AC voltages and currents. I think it's always very good to use a voltmeter for the simple reason that it will give you the right polarity for the voltage. You can't really get it wrong. So I'll just press Ctrl L and then type V_meter, and I will place one of the input like so. We can click on the View All button to get a bit more space, and we'll then change the ID to VIN and then connect it across our source like so. Then we can simply press Ctrl C and Ctrl V and place another voltmeter right at the output like so across the load resistor, and then call this VL. Then click on the View All button to see everything again. The other thing that we may want to do is connect a voltmeter that gives us the voltage at the emitter. In this case, because it'd be a little bit cumbersome to have a voltage meter put in here and it would make things a little bit too messy, I'm going to use an M probe instead, a measurement probe, and I will call the voltage here VE. So it's very important to use the correct labels for each of these measurement devices so that we can't really get it wrong when we go and plot it. So now you need to perform a number of calculations which we have formulae for in Appendix 1 of your handout. What I will do is show you how to plot the various waveforms that you need to analyze to get your numbers to plug into the equations in Appendix 1 and calculate all the various parameters that you're given in the handout. So first and foremost, we've got IC, so the current that flows through the collector. Now, because we want to measure the AC current, we can no longer use an annotation here. So what we need to do is insert a current meter in series with our collector. So simply remove this wire here and that wire there, and then press Ctrl L and type in I_meter. Then right click on this until the current points in the right direction. Current will be flowing into the collector. Change the ID of this meter to IC so you can easily recognize it, and then of course you have to re-establish the connections that were there before. Now you're able to measure IC, and once you've measured IC, of course you have to work out its average, and then by using the average of IC and by using the supply voltage, you'll be able to calculate PSS. So let's go on to graphs, right click on graphs, create new graph, and then just call it collector current. Now the current that we will get here will be the total instantaneous current, and this will be represented in terms of equations by the lowercase letter I and the uppercase letter C, because we're talking about total instantaneous value of the current. So let's simply right click on this graph, go on to add a new measurement, and then we'll have to go to nonlinear and current, and then we will find I time. So we want a time waveform of the current, and then we need to select what measurement component we'll get it from. As you may remember, we can click on the three dots, the schematic opens up, and we can pick the component that we want. In this case, it will be our emitter called IC, and then click on OK, and then we simply click on apply, and then OK. Then simulate. Now you can see the waveform that you get for your current, and intuitively this looks right to me, and that is because we have a DC offset for the current, which is roughly 50 milliamps, and then superimposed upon that DC offset we've got a time varying waveform of a specific amplitude. So this is what you should be seeing. You bias your transistor to have a collector current around 50 milliamps, and this should be the DC bias that you observe on your waveform when the transistor is operating with an input signal, which is varying with time, like a sinusoidal signal. Now there are a couple of things that we can do to make things look a little bit better here, and that is we could change the units for the frequency and we could change the units for time. So how do we do that? We go to project options, and then we select the global units tab, and then we select our frequency to be in kilohertz, and also our time to be in some bigger unit, let's say milliseconds. That should do, and then we resimulate, and now you can see that we've got time in milliseconds here, the frequency is now in kilohertz, and that makes things a bit more legible. For the PSS calculation, what you need to find out is the average collector current. Now the collector current is a sinusoidally varying quantity, so the average will always be equal to the DC offset that you have. If you had no DC offset, the average of a sinusoidal current would be 0. If you have a DC offset, the average of the sinusoidal current will be equal to the DC offset. So roughly here what we get is about 50 milliamps, which is exactly what you bias the transistor to. If you wanted to measure the peak-to-peak value of your waveform, you simply right-click and select Add Marker and add one here, and then again right-click, select Add Marker again and add one over there, send one to the maximum, one to the minimum, and then select one of the two as your reference marker. And then you can basically say that the waveform that you've got for the current at the collector is a waveform of an amplitude of about 33 milliamps peak to peak, and also a 50 milliamp DC offset. So this allows you to calculate PSS. Let's move on to the load signal power. You've got the equation there that allows you to relate the peak amplitude of your load voltage to the load power through the load resistor. So we can simply create a new graph, and we'll call this load voltage, and then we right click, select add a new measurement. In this case it will be a voltage, and then we choose V time, and again we click on the three dots and we select the V meter with an ID of VL as our measurement component. Click on OK, and then apply, and then OK again, and simulate. In this case you can see that you have a 0 offset, there's no DC offset, and this is quite obvious to see because if we go back to the schematic, we have a capacitor here that does not allow for any DC current to go through. Because of that, any DC offset is removed by our capacitor, and hence all we see here is a simple AC voltage which has a mean of 0. It's much the same thing as doing coupling AC on an oscilloscope. So if we go back to our low voltage, you can see that we have an amplitude of roughly 2 volts peak to peak, as I predicted. So you can see that in order to get an amplitude of about 2 volts peak to peak in output with a common collector emitter follower, all you have to do is basically apply a 2 volts peak to peak signal at the input. So now you can calculate the peak value of VL by simply right clicking, selecting add marker, put a marker in there and then go marker to max, and this will give you your VL hat, let's call it, which is the peak amplitude of the load voltage. Now let's have a look at the emitter voltage instead. If we go back to the schematic here, you can see that the voltage for the emitter we are measuring on this side of the capacitor, and hence because we haven't got any way to filter out DC, we can expect that the voltage, the AC voltage that we see here, will have some sort of DC offset. So let's verify just that. Click on graphs, go on to new graph, and we call this emitter voltage, and then we right click on it, create a new measurement. It'd be again a voltage V time. In this case the measurement component will be our M probe, and then click on OK and apply, and then OK again. Then click on simulate, and lo and behold, we do have a DC offset in this case. We didn't have it across the load resistor because that was removed by the capacitor, but we do have it in this case. So for your calculations you will need two quantities. Firstly, you need the quiescent value for the emitter voltage. That is the bias voltage that we saw before, and is nothing but the DC offset that we observe on this curve. So if you look at this curve, you can see that the DC offset is roughly 7.5 volts, and this will be your quiescent emitter voltage, VEQ. Then look at the notation that you've got here. When you are calculating PES, you've got a capital letter for the voltage, but a lowercase letter for the subscript. So when you're asked to look at VE peak, when E is a lowercase letter, all they're asking you to give them is just the AC component. To calculate that, all you need to do is simply select add marker, place one at the top of the waveform, just like so, and then again place another one down here, and again you send this one to minimum, you send that one to maximum, and then you select one of the two to be your reference. So you've got a delta of about 2 volts. Since this waveform has got a 7.5 volt DC offset and an amplitude peak to peak of about 2 volts, your peak amplitude, VE peak, is only 1 volt. So to calculate your PES, what you have to do is use this value of 1 volt for the peak AC voltage for the emitter, and then divide that by 2 times RE. Now, as you've seen with op-amps, it comes a point when you increase the input signal amplitude that you get clipping on the waveforms, because the amplifier can no longer supply enough voltage for your waveforms to be undistorted. In Macro Office, it's very easy to find out the point when distortion starts to occur. So let's see how we do this. First of all, let's go back to our Class A amplifier schematic, and now we make the amplitude of our input signal tunable. This will allow us to then change the amplitude until we observe some sort of distortion. Then we'll set up another graph. We'll call it VL and VIN. And then we add 2 measurements here, both voltage measurements. One would be our input voltage, then click on apply, and the other one will be our load voltage. Now if we simulate, you can see a direct comparison of our load and input voltages, and you can see that the amplitude is pretty much the same. The load voltage, if you notice, is slightly smaller in amplitude. This would be the pink curve. Now what we can do is simply open the tune tool here, and then we can select a range which is sensible. Let's say that we start from 1 and we go up to 5, and let's do that in increments of 0.1 volts. And we need to get to a point where we start to observe some sort of distortion in the waveform. This is quite easy to spot, because now you can see that the two curves maintain the same relationship all the time. One is slightly smaller than the other, but as I increase the voltage, again that relationship remains more or less the same, up until we get to a point where one of the two waveforms starts to get much smaller than the other, as you can see here. Now, the other thing that you can see is that you get this kind of hump here. And this is something that I left in there on purpose, because if you leave everything as a default in Microwave Office, this is what will happen. This is due to the way it's simulating the waveforms, which is more suited to radio frequency signals than AC signals. But this can be easily rectified. So simply right click, go on to Modify Measurement, and choose your VL. And then instead of using Uplug HB as a simulator, change this to Uplug Transient. For consistency, also modify the V-in measurement so that the simulation engine that is used for that is also Uplug Transient. And then simulate. Now you can see that the waveform you're getting doesn't have those humps that the other one had. So what we need to do here is basically just find the boundary condition where clipping starts to occur. And you can see that about 2.9 volts, this is when things start to go wrong. So if I increase above that, you can see that the bottom of the curve is starting to flatten, the bottom of the load voltage that is, and then this gets worse as we increase the input signal drive. As we go back down, we get to a point where the load voltage becomes sinusoidal again, and about 2.9 to 3 volts is our limit. You may find a slightly different value, plus or minus 0.1, 0.2 volts, it doesn't really matter. But the important thing is that the VLM hat value, which you're asked to find in section 312, will be around 3 volts. Now the exercise asks you to keep the input drive at this very value, the value that gives you the maximum amplitude you can possibly achieve without distorting the load waveform. Now all you have to do is repeat the same calculations as you did before, and you will be able to use, of course, the same graphs that we used earlier. So you have a load voltage there from which you can work out your peak load amplitude, and also you have the emitter voltage, which allows you to work out your DC bias offset, and also allows you to work out the peak value of the AC part of the emitter voltage. And with all of those, you should be able to carry out all the calculations necessary. The lab exercise then asks you to draw the waveforms for different currents for your circuit. And we've seen how this can be done. All you need to do in order to accomplish that is to put current meters in series with the right elements, and then you should be able to simply plot the current as we have already done for the collector current, for instance. So this should be quite an easy thing for you to do, and I'll leave it for an exercise. It shouldn't be at all difficult to carry out. In section 314, the exercise asks you to observe VE and VL using a DC coupled oscilloscope. And the reason why we do that is because we want to be able to see the offset that one has and the other one doesn't have. In our case, I will use a little bit of a trick to set up this measurement. Right click on graphs and then create a new graph, a rectangular graph, call it VE and VL, and then click on create. And then what we can simply do without setting anything up, we already have these measurements in other graphs. and we can simply drag them to duplicate them. What we do, we've got the emitter voltage here, you just drag it on top of your new graph, and there you go. And then you've got your emitter voltage transferred to that graph, or rather copied to that graph. And then we also have the load voltage over here. Just click on the measurement, hold the left button and drag onto this graph here, and then you've got the two in the same graph. So this is quite a nice quick way to do things. If you want to create a graph with a combination of various measurements that you've already set up, simply create the new graph and then drag the various measurements onto it so as to create the graph that you want. So hopefully this will give you enough information to simulate every single part of the Class A section of the Amplifier lab. And hopefully we'll manage to put together a subsequent video for your Class B part of the lab.